This morning, we're welcoming Mohammed Abubakar of Shafii Health Sciences University, who will be presenting on pairwise networks in epidemiology, giving us a review of approximations, dynamics, and applications. Mohammed is currently a PhD student at the university in the departments of mathematics and applied mathematics, which is where he also completed his master's, graduating cum laude honors. His research interests further include QSPR models, computational graph theory, and machine learning. And he is already very widely published. So thank you so much, Mohammed. I'll hand over to you now. And thank you again for joining us.
Good morning. So my name is Mohammed Shafii Abubakar, and today I'll be presenting on pairwise network models in epidemiology. And as Diane rightly introduced, I'm a PhD student at Shafii Health Sciences University. I'm supervised by Dr. Kazim Aremo and Professor Maggie Apani. So today I want to take us through a short review on the intersection between network science and epidemiology. So we are going to start with the definition of a network. A network is simply an applied graph. So a network can be defined as a structure, composed of interconnected entities called nodes, and which is linked by edges. And then these networks, they are classified according to, their structural complexities, their applications, and generation mechanisms. So we have different types of networks. We have the random networks, where links between the nodes exist with certain probabilities. A very good example of this random networks is the Erdos-Renyi, network, which is also known as the ER network. We have the scale-free networks. These scale-free networks are characterized by existence of hubs or nodes with very high degrees. We also have the small world networks. These are networks that are characterized by short average path lengths and very high clustering. We also have the regular lattice networks, which is the same as the regular graphs. In this type of networks, every node in the network have equal degrees. We also have the community or modular networks, where nodes are organized into distinct groups or classes. Additionally, we also have the multi-layer networks, which is sometimes called the multiplex networks. So the multi-layer or multiplex networks are characterized by existence of multiple interconnected layers. So these are, some of the types of, networks, that we have. And then here I have a very small simulation. The first figure on the left is the scale-free networks. So just like I mentioned earlier, you can see here we have some nodes with very high degrees. So these nodes with very high degrees are known as the hubs. So and this is one of the major characteristics of the scale-free networks. So the scale-free networks is used to model the real world social networks, because it is believed that even in reality there are certain individuals or there are certain places in our communities that have a high number of connections, such as marketplaces, hospitals, schools, and so on and so forth. So in order to model real world networks, the scale-free networks, is very, very, good in terms of that type of modeling. So, and then we also have a graph that shows the degree distribution of the scale-free network. So, and on the right-hand side, we have the small world networks. So the small world networks is another type of networks, that can be used to model social networks. Also, although unlike the scale-free networks, the small world network is characterized by existence of, average short path lengths, and it also has a very high clustering. So now coming into the ideas of pairwise models. So in order to study, these networks, or to be able to model these networks, there are certain approaches that we use. We have different types of models that we use in, modeling, these networks. We have the age-based compartmental models, we have the pairwise models, we have the agent-based models, and so on and so forth. So, but, my talk is today is focused on, these pairwise models. So from the word pairwise, it is characterized by the existence of pairs in the network. So once we have connection between one or two vertices, these connections are called pairs. So we want to study how these connections form over time and how they are able to impact the spread of diseases in the network. So the ideas of pairwise model was first conceptualized in the work of Levin and Penn, and then later, this idea was popularized by the likes of Rand, Killing in the late 90s. And then we also had other, researchers such as Eames, Bouch, Chris Bouch, and the rest of them who have done, a lot of very good, works in this direction. So one of the reasons why these pairwise models came into existence was to, correct some assumptions in the classical deterministic mean field models. If you look at the classical deterministic models, the ones that were, introduced by Carmack and McKendrick, the SIR model, and the rest of them, they assume that, contacts or individuals in a population are well mixed, they are random. So, and then due to this, they only seek to model the number of individuals in each compartment. So you see that in an SIR model, what they normally model is the number of people that move from the susceptible class to the infected class, and the number of people that move from infected to recovered. So, but, in network models or in pairwise models, we are more interested in how individual level interaction, how the interaction between, individuals in a network is able to impact, the spread of diseases. So for example, one of the assumptions in pairwise model is that a susceptible person is more likely to be in contact with an infected individual if they are in a household or a social cluster. So unlike the deterministic model, which assumes that, individuals, all the total number of individuals in the population are well mixed, meaning that, individual maybe in this community has equal probability of meeting with individual in that community. So you see that in reality, that is not the case. In reality, we are more likely to be infected with a disease with, someone whom we share an office with or someone who we share an apartment with than someone who is far away in Joburg. So pairwise model seeks to capture this, peer level interaction, which, at the end of the day, improves realism while keeping the model relatively simple and analytically tractable. So a pairwise model is a type of mathematical model that is used to describe the dynamics on a network, and also it explicitly accounts for correlations between pairs of, connected nodes. So, what pairwise models normally do is that it also helps us to capture local correlations in the networks, and then which reflect how the infection probability of susceptible individual depend on the infection status of its neighbors. So the belief is that, when we have, let's say when we have two connected individuals, susceptible individuals that are connected, these individuals might never be infected unless, they come into contact with an infectious individual. So having two susceptible individuals connected, that is called a pair. But when one of these susceptible individual is now further connected to an infected individual, then in that case, we have, what we call a higher order interaction. So one of the things that we want to do in pairwise model is that the formation of these higher order interactions at the beginning of an epidemic is what we want to really look at. How do we approximate these higher order interactions that form? Because higher order interactions comes in various forms. We can have triple, just like we have here, SSI. We can even have, in some cases, quadruple, where we have SSII or SSIS, depending on type of compartmental model that is, being studied. So whenever we have the formation of higher order interactions, how do we approximate them in order to have an analytically tractable solution. So here we have a small visualization of a network and how this network how other interaction affects formation of network. So if you look at on the left hand side, we have a network of 100 nodes with a clustering coefficient. So this clustering coefficient, it's a parameter that is used to analyze how triadic structures form in a network. And then these triadic structures, you can see I have it below in figure 3. If you look at figure 3, the first figure there has ABC. ABC is a higher order interaction. It is a triple where A is connected to B, B is connected to C. But we can further connect these structures, forming even a more higher interaction where we have A connected to B, B connected to C, and C connected to A. So this type of formation is known as a triangle, or in some cases, we call it a cluster. So one of the things we also wish to study in our approximation is, the impact of these clusters, on the spread of diseases. How does clusters, impact the spread of diseases? Does it slow down the spread of disease? Does it, increase the spread of disease? So if you look at the simulations in figure 2, on the left-hand side, we have a network with a clustering coefficient of 0.189. So there you see that the clustering coefficient is very low. So, and then that is why you don't really see, a lot of, triangles in that network. But coming to the right-hand side, we have a clustering coefficient of 0.438. And then you see that triangular formations, is more visible in that network. So the higher the clustering coefficient, the better the formation of triangles in that network. So our pairwise network models can be studied in two frameworks. Number one, we have the homogeneous degree networks, which can be studied on regular lattices or uniform random graphs. We also have the heterogeneous degree networks, which can be studied on power law distributions or scale-free networks and exponential distribution. So homogeneous degree network works with the assumption that, all the nodes in the network have an average degree, while heterogeneous degree networks works with the assumption that all nodes in the network, have different degrees. So now coming down to the study of approximations. So one of the earliest approximations that was studied in these directions, was in the works of Sato, Matsuda, and Sasaki. So in their work, they were able to study the SIS, compartmental model, and then the formation of, triples in that network informed their choice of approximation. So they came up with an improved pair approximation, which is also known as an ordinary pair approximation. But in their ordinary pair approximation, it did not account for clustering. So that means we do not have formation of triangles. Rather, what we have is just the formation of triples. So the first equation in which they approximated, they said, okay, if you have a triple, let's say ISI, how do we approximate these triples in an homogeneous network? So that approximation was given by 1 plus n minus 1 over n times n into I, s. So where n is the average node degree, I is the infected node, and S is the susceptible node. So, and this is also equal to 1 plus n minus 1 over S divided by n times S per SI divided by S. This SI divided by S is simply the average number of infected neighbors per susceptible, individual. So one of the limitations of these approximations was that it did not account for, clustering, and then since it was an homogeneous network, it was tested on regular lattice structures. So later on, the triangular pair approximation was introduced by Morris in his PhD thesis, and then this triangular pair approximation is one of the most efficient approximation that is still in existence in literature up to today. I think this work was done in 1997. Yeah. So his triangular pair approximation, is here. It takes into account, clustering or triangle formations in the network. So what it's saying is that if you have a triple ABC, how do we approximate this triple? How do we break down this triple so that we represent the entire system in terms of pairs? So if you look at the first part, we have n minus 1 over n times pair AB times pair BC divided by, divided by B. So here, what it is saying is that in order for you to break down this triple, you take the pair between A and B, multiplied by the pair between B and C, and then divided by the central node. And then in the bracket, we have 1 minus phi. 1 minus phi is the probability that, the network is not clustered. But now, if we want to now check the clustering part of the network, which is given by the second term, we have phi times n times the pair AC divided by n times A times C. So n is the total number of nodes in the network, n is the average node degree. So if you look at that part, phi, it is giving us the probability or the proportion of triangles that exist in the network. And then he defined this clustering coefficient phi as the summation of triangles ABC divided by summation of triple ABC. So although one of the limitations of this clustering coefficient was that it required explicit tracking of the number of triangles and triples in a network. So if you have a very large network, it becomes very complex. So and then Rand also introduced his own approximation. Although, what Rand did was that he utilized, the triangular pair approximation that was introduced by Morris, and then he added, an additional correction term, which is T times AB, which is seen in equation 4, which is T times AB. And then this T times AB, is an assumed, value that is usually obtained from simulations or data that is available. So, and then this Rand approximation in equation 4 only seeks to approximate the number of triples in a network. It does not really consider the number of triangles. And then now coming into the works of Killing in 1999. So Killing was the one that what Killing did was that he introduced one of the most efficient clustering coefficient, that is in existence in the literature up until today. And then he also studied, the impact of this clustering coefficient on an SIR, network model. So as you can see here in this figure, we have a flow diagram for a network SIR model. So if you look at the first flow here, we have the SS pair. So what this is saying is that, given two susceptible nodes, the chances of this susceptible node, of any of this node being infected, is dependent on a triple. That is, it is either one of the nodes is connected to an infected node, to an external infected node, and this external infected node can lead to the infection of one of the S nodes. So at a rate of tau. So that is why we have tau times the triple ISS. And then, we also have IS. When one of the susceptible node is now infected, two things can happen. It is either one of the S node becomes infected so that we have the breaking of the IS node to form II node, or the I node that was initially infected becomes recovered at a rate of gamma. So, but if you look at the flow between IS and II, you see that there are two arrows there. So the two arrows, what it represents is that, number one, it is either the other S node becomes infected because its neighbor is infected, or the other S node becomes infected because it is also connected to another infected node, which forms the triple tau ISI. So, and then this is the framework upon which the SIR model, was constructed by Killing, and then this led to the model equations that we have in equation 5. So if you look at our equation 5, you'll see that in the model equation, we have triples, SSI, we have ISI. So what we normally do here is that whenever we see these triples in the equation, our objective is to approximate these triples in terms of pairs so that we have an analytically tractable solution. So, and also the clustering coefficient that was introduced by Killing is given in equation 6, and it utilizes the adjacency matrix. So it is simply the ratio of the number of triangles to the number of triples, and it utilizes the adjacency matrix of the graph or the network. So here G is the adjacency matrix. So, and the trace, and G cube simply seeks to analyze the number of triples that exist in the network. G squared seeks to analyze, G cube seeks to analyze the number of triangles in the network. G squared seeks to analyze the number of triples. So trace of G cube is simply the sum of the diagonal element of the matrix G cube, and then the norm of G squared is simply the summation of all the elements in the matrix G squared. And trace of G squared is simply the sum of diagonal elements in the matrix G squared. So when you have trace of G cube now, it gives us the number of triangles in the network, and the norm of G squared minus trace of G squared gives us the total number of triples that exist in the network. So this clustering coefficient was incorporated into the triple approximation that was introduced by Morris. So it was incorporated into this triple approximation. So, but in the absence of clusters, that is, if our phi is equal to 0, then you see that this equation 1 is going to reduce, to just the triple part, of the approximation. So, and then which you can see here, the dynamics of SI, we approximated it using the Morris triple approximation, and while incorporating the Killing clustering coefficient. So now, in order to obtain the, after we've simplified the system, we've broken down the triples. One of the things that is done in this area is to obtain the epidemic thresholds. So, and unlike our deterministic model, whereby at disease-free equilibrium, we normally at disease-free equilibrium, the correlation between susceptible and infected individual is by random mixing. Here, in pairwise models, what happens at the beginning of the disease, or at the beginning, at disease-free equilibrium, is that the formation of pair correlations begins to form. So the formation of pair correlations begins to form, and then this pair correlation, for example, we have the correlation CSI. These are some of the first pair correlations that we form. And then later we can have the pair correlation CII, and then CEI if it is an SEIR model, and so forth, and so on and so forth. So, so at disease-free equilibrium, when the number of infected in the network is equal to 0, we have the formation of these pair correlations. So in order to obtain the early epidemic growth or the basic growth rate, we have to find the dynamic of this CSI. So, and then when, Killing solved for the dynamic of CSI, he discovered that this dynamic is dependent on another pair correlation, which is CII. So he had to also solve for CII, which is given in the equation above 9. And then after solving for CII and he got this quasi-steady state, variable, he substituted that into CSI and then solved that system at equilibrium when the entire system is equal to 0. And then when he solved it, he was able to obtain his R naught. And then from that R naught, he was able to, infer, he was able to give some conclusion based on, the R naught that he obtained. So one of the conclusions is that an epidemic can occur if and only if n is strictly greater than 2, that is, if the average node degree is greater than 2, then we will have an epidemic occurring. That is, each individual in the network must have a degree that is greater than 2, for an epidemic to occur. And also, the clustering coefficient must be greater than n minus 2 divided by n minus 1. So he said increased clustering coefficient always act to suppress the invasion. So, so here he was able to tell us the impact of clustering in the network. That is, when you have increased clustering in the network, it helps to slow down the rate at which this disease is spread in that network. And then at the end of the day, he was able to carry out some, complex network simulations on, I think, Eridus-Renyi network, and so on and so forth. So, and then coming down into, I think, 2010 or 11, EAMS developed a kind of hybrid pairwise model, that was able to combine two types of contact. So number one, it was able to combine the regular contact and the frequent contact and the infrequent contact. So here, so here the total number of degrees or contact in the network is given as Kn plus Km. So where Kn is the average, number of contact in the network, and Km is the random contact in the network. So this random contact, can happen. Maybe someone whom you just met frequently at the market, that is a random contact. But average contact, the people, or the regular contact are the people whom you share, household with or offices with. So what he was trying to do here was to, introduce a more realistic approach to this pairwise model, such that we are not only considering regular contact, but we also want to consider, the random contact. And then he gave this approximation. The approximation was also based on the approximation by Morris. But if you look at this clustering approximation, we have the triple part on the left, and then the clustering part on the right, which is also scaled by P divided by K, and where P is the total, is this sum of S plus I plus R, that is the total population in the network. So, and then at the end of the day, he was able to obtain a deterministic model. This is the deterministic pairwise model that is given in equation 11. And then after that, he was also able to compute his early epidemic growth rates, by using, the formation of this pair correlation. So one of the formation of pair correlation that he observed when he set the dynamic of the infected class, when he tried to solve the dynamic of the infected class, one of the early correlation he obtained was Si over I, which was represented as lambda. So in some cases, we call these lambdas fast variable, because these are variables that changes very rapidly, during the initial, during the beginning of an epidemic. And then after he obtained this early epidemic growth rate, which is given in equation 12, he further went ahead to solve for the final R naught of the pairwise system. So the early epidemic growth rate, mostly it is usually computed from the single, class of the pairwise dynamic, and then the final R naught is usually computed from the pairwise itself. So, and then we have the work of Barnard. The work of Barnard was in 2020, 2019, 2020. So Barnard was able to introduce an improved closure approximation that was able to address some issues of normalization in the approximations of Killing, Morris, and the rest of them. So his own approximation is a little bit more complex than that of Killing. And then he was able to use this approximation given in equation 14, to model the dynamic of SIR. So, and then you can see in equation 15, he aimed to study the, he wanted to compute the early epidemic growth rate, by considering the dynamic of the single, individual, of a single individual who is infected. And then he came up with this quantity, which is tau Si over I. So at disease-free equilibrium, you see that if we set Si to be equal to 0 and we set II to be equal to 0, we are going to obtain an undefined quantity. So rather, what he did was that instead of obtaining an undefined quantity, we can represent this quantity Si over I as a fast variable. So he represented that Si over I as the variable alpha, and then he solved the dynamics of alpha. And then after he solved the dynamic of alpha, he discovered that the dynamic of alpha was dependent on dynamic of delta. So delta is II over I. So he had to also solve, the dynamic of delta. So, and then when he solved both, he was able to obtain the system of equation given in equation 19 and 20. And then from that, we can see that these equations are nonlinear. He had to use perturbation approach, to obtain the value of alpha, the quasi-steady state value of alpha and delta, and then he substituted delta into alpha, since alpha was dependent on delta. And at the end of the day, was able to obtain, the basic growth rate, which is tau n minus 2 over gamma, as given in equation 23. And then after he obtained this basic growth rate, he also went further, to solve for the R0 and final epidemic size using the pairwise part of the model. And then he performed, simulations on some, regular random graphs and homogeneous degree networks. So now we are going to come to the second part of the pairwise network model, which is the heterogeneous degree, network. So the heterogeneous degree network, as I mentioned earlier, this is a network whereby the nodes in the network have different degrees. So for example, you can look at, in the case of SS here, we have one of the susceptible node having degree K and another susceptible node having degree L. Now, now for any of these susceptible node to be infected, of course, they have to be connected to an external infected node. So you can see there, we have an external infected node. We have ISKSL, with transmission rate of tau. So, and then there, I is not given any degree, to show that, yes, I is an external, node that is not part of, this pair. So, and then using this flow diagram, they were able to obtain some model equations, which are used to solve, various epidemiological parameters. So based on this heterogeneous network, House and Killing also further introduced another kind of pairwise approximation that is able to handle, the case of heterogeneous, degree networks. So here, when you have a triple AKBLCM, it can be approximated by L minus 1 over L times the pair AKBL times the pair BLCM divided by the center node BL. And then 1 minus phi is the probability that the network is not clustered, and then the part of phi is the probability that the network is clustered. So in that part, we are also considering the edge between the node CM and AK. So, and in the absence of clustering, this is going to reduce to the simple, triple approximation, which is given in equation 25. So, and then Keys et al. Further utilize this flow diagram here to solve, to solve the pairwise model equation for an heterogeneous, network, model. So, and then before he was able to solve for his epidemiological parameters, first what he did was that he gave some simple approximation. For example, if you look at for the single, okay, yeah. So if you look at for the single compartment that is given above, for an individual compartment SK to become infected, of course, it must be connected to an external node, to an external infected node, I. So that I, the degree is not given. So that I could be a node of any degree. So it is very, very important for us to approximate this SKI. So that was the first approximation that was given by Kiss. So here, Kiss gave the approximation that SKI can be approximated by K, which is the node degree for the susceptible node, and then times SK, which is the number of susceptible nodes in the network, times pi I. So pi I now is simply the the ratio of the number of connections or stops that are coming from infected node divided by the total number of nodes that have a particular degree in that network. So for example, if let's say our infected node has different stops, so these stops have edges. If it have different stops, let's say it have a stop of L, M, and so on and so forth. So we are going to sum up all these different stops that are present in the infected node, and then divided by the total number of stops with that particular degree in that network. So that this approximation is used to simplify SKI, and then which is also further approximated as NKL divided by NK times NL times the SK times I. NKL is simply the number of connection between degrees K and L. NK, capital letter NK, is the total number of nodes with degree K, and capital letter NL is the total number of nodes with degree L. So, and then using this approximation, he was able to obtain the first epidemic threshold, which is tau C, which is the critical transmissibility, which is given in equation 31, where we have the average degree K divided by the second moment of the average degree K squared. So, and then since the network was an heterogeneous network, it performed complex simulations on scale-free networks and also on Erdos-Renyi networks. So, and then these are some of the, important, approximations that have been given in pairwise model. We also have others, that have been given by some other researchers. So, but also the study of this, pairwise network models is evolving, and then a lot of people, are coming into this area with different ideas and also with different types of interaction, because what pairwise model seeks to do, it seeks to model, how interaction, can impact, the dynamic of a system. So there are some recent works that have also been, done. For example, we have, the prediction of disease-induced herd immunity. That's is a mistake there, which was also done by DeLauro et al. In 2021. And then pairwise models have also been used to model protein interaction networks. This was in 2022. And then also in 2022, we've seen the modeling of multi-strain interaction, whereby you have, more than one, disease interacting within the human system, at the same time. So we want to see here, what they did was that they want to see how, this disease, affect, the other disease. For example, we can look at the case of HIV tuberculosis co-infection. This can be modeled, via, pairwise model. And then also in 2022, it was used to model behavioral responses. This was by Jing et al. And then, most recently, Keys, Bathouse, and Kudabuch, were able to incorporate survival analysis to model epidemic data, using, this concept of pairwise models. So there are a lot of, things that are coming into these directions. And, finally, we have some future directions that we can look into in this study of pairwise, network models. For example, we can look at higher network structures. We can extend these models beyond triads to include 4-node motifs, although there are some researchers, that have done one or two in this direction, but a lot is still needs to be done. And then also, it can also be useful in multi-community and zoonotic system. So maybe where you have transmission of diseases from animals to humans, or cross maybe both humans to animals and animals to humans. So this type of zoonotic transmission can also be considered in pairwise network models. And then also in the study of intercommunity mobility, interspecies transmission and multi-pathogen infections, we can also use pairwise models. So in terms of intercommunity mobility, we can actually look at how human migration affect the spread of diseases. For example, you see that during COVID-19, initially there was a mass migration of people. Some were going back to their countries, and then later it stopped. So we can also look at how these migrations, affect, spread of diseases. So, and then also we can integrate advanced data into these pairwise network models, to do a lot of things. We can apply statistical inference to reconstruct contact structures and calibrate parameters, and also forecast outbreaks in real time. And then lastly, we can incorporate contact rewiring, adaptive strategies, and risk-based, responses, to model, the spread of diseases in a network. And then these are some of the future directions, one can look into in pairwise network models. Thank you very much for listening.
Thank you so much, Mohammed, for the lovely presentation. Thank you for taking the time to present.
Thank you.
We hope we will have more presentations. But in the absence of any questions at this juncture, we will now consider the seminar officially ended. Thank you so much, Mohammed.
All right, thank you, sir.